Hi everyone, I am Sudan. I'm a graduate student working with Professor Leela Araba at Wayne State University, Michigan. In this presentation, I'm going to talk about understanding the cathode electrode interface formation on the lead NMC cathodes operated at extreme environment. The main motivation of the work is that conventional lithium batteries can be operated between room temperature and just above room temperature. Operation beyond the suggested temperature range will lead to irreversible degradation, in some cases catastrophic failures such as fires and explosion. Many industrial applications such as sensor, military applications, gas and oil and gas drilling applications that need lithium batteries to be operated beyond 60 degrees Celsius, in some cases 100 degrees Celsius. Fundamentally, the electrolyte interface is the main source for degradation in terms of cathode. Cathode electrolyte interface is crucial. That understanding at high temperature, cathode interface chemistry, understanding at high temperature is not well understood. Therefore, we investigated layered NMC model NMC cathode in a thermally stable ionic liquid environment, and we investigated the surface and bulk properties using various spectroscopy and microscopy probes. As you can see in the electrochemical investigation, we investigated the NMC cathode in ionic liquid electrolyte. We conducted the electrochemical charge discharge studies, and as you can see, the NMC cathode was severely degraded at high temperature operation at 100 degrees Celsius. Even though the ionic liquid is thermally stable, the electrochemical interaction at high temperature is not favorable. So after several studies, we hypothesized that if we stabilize the NMC surface using a thermally stable cathode electrolyte interface, that will reduce the contact between a direct contact between electrolyte and cathode surface. So that will improve the electrochemical reactions. So we attempted that approach, and the approach was successful. After adding the LiDFOB, that is one of the additives in lithium battery community, lithium difluoroxylate borate, that additive improved the high temperature performance at high temperature performance at 100 degrees Celsius. So after that, we wanted to understand the surface of the NMC using hard X-ray photoelectron spectroscopy, using different photon energies. We use different photon energies to understand the cathode interface at different depth levels. The take-home message from oxygen 1s spectra, the take-home message of the oxygen 1s spectra is that at high temperature during initial cycles, the cathode interface formation was accelerated. And from F1s spectra, fluorine 1s spectra, we clearly see that the boron-based surface species are emerging in the surface regions compared to deeper surfaces. So we supported that with the boron 1s spectrum, and as you can see, at high temperature during initial cycle, the boron signal is intense compared to other sample conditions. After this chemical understanding, we wanted to visualize the cathode electrolyte interface, and as you can see, we investigated with HRTM analysis. As you can see, the pristine cathode is free from surface layers, and the pure ionic liquid without any additives, the cathode was cycled at high temperature, and that cathode was degraded, and that, as you can see, the surface was severely degraded. But after protection, the nanoscale interface layer is here, that is protecting the surface from electrolyte attack. And we wanted to confirm that the degradation phenomenon is majorly from surface region. So we investigated transmission mode bulk sensitive Zan spectra, and here we have confirmed that the nickel is the redox couple in NMC cathodes. That was confirmed using Zan spectra, different state of charge. So this work, based on this work, we have obtained various conclusions. The first is that the obtained capacity is purely from nickel redox couple, And the cathode interface formation is accelerated at high temperature, and the passivation layer is protecting the surface from electrolyte attack. So if we understand the rationality of the science, we'll be able to develop high temperature stable additives and high temperature stable ionic liquids for high temperature lithium battery applications. And I want to thank this work was primarily this work used resources primarily used resources from CFN NSLS-II, and and also we used resources from APS. And I want to thank staff members from CFN, NSLS-II, and APS, and our funding partners. Thanks for giving me this opportunity. Thank you.